Our next speaker is Tuan Tran.
Yes.
And it's on Elastic Video Content Delivery Networks at the Edge.
Yeah. Thank you for the introduction. Hello, my name is Tuan Tran, and today.
So it takes a couple of.
Okay. Yeah. So, today I'm going to talk about the virtualized video content delivery networks that are deployed at the edge of the mobile network. That's we call it VCDN. This work has been done with my colleagues, Christophe Newman and Guillaume Bichot. Mobile network operators start using more and more edge platforms to deploy their network functions and services as a virtual appliance within their mobile network. The edge platform, which are geographically distributed across the mobile network, provide a great flexibility for virtual resource utilizations. More importantly, the edge platform allow to deploy the virtual applications as close to the end user to improve the query. From video streaming perspective, delegating the streaming content to the CDN cache instances deployed at the edge improves the query. We all know that. However, deploying the virtual application at the edge imposes a certain cost, such as infrastructure, egress traffic cost, etc. So, continuously running the VCN cache instance at the edge location is a waste of resources. That's why we think that the VCN system must continuously adjust its virtual infrastructure in order to optimize the trade-off between the cost and the query provided to the end user. This figure showed that the cache instance can be deployed anywhere within the mobile networks. For example, it can be in the central just before leaving the mobile network to the internet, or in the middle, or even net to the mobile base stations. So the term edge means that anywhere within the mobile network. So to build such a VCN system, we identified 4 important requirements. First, the system should be virtualized, so which means that it should be designed to be deployed on the Kubernetes-based edge platforms. Kubernetes is now de facto industry standards. So this design allows to take advantage of Kubernetes built-in features such as automatic scaling, self-monitoring, etc. Second, the system should be elastic, which means that the system should be able to dynamically create or terminate any cache instance based on different application metrics and costs. An elastic system should be able to deal with the peak of traffic by using both vertical and horizontal scaling. The horizontal scaling means to deploy the cache instance in more edge locations, while vertical scaling means to deploy more cache instances in the same edge locations. As a VCN system dynamically create cache instances or the score is dynamically, so the systems must be able to migrate ongoing streaming sessions from one cache instance to another one without interfering with the end user experience. For example, when a new cache instance is deployed, some existing streaming sessions are relocated to this new one because they are physically closer to this new cache instance. And the mobile network has a particularity that the mobile user may move between the cells, and that triggers the handover procedure. The handover and the mobility events may cause the packet loss or disconnection for a period of time. So it is required for the VCN system should be resilient to the events to ensure a smooth video playback. So let's take a look on how the VCN concept works. In this figure, on the top left, there are 2 mobile users watching the same content from the content provider A. So these 2 mobile users are enough to justify a deployment of a cache instance in H1 location on the top. On the bottom left, there's only 1 mobile user, so it is streaming with the cache instance in the central. Later, 1 mobile user from the H1 moved to the H2 locations. And so the H2 location now has 2 mobile users, and the system decides to instantiate a cache instance in S2 to serve the two mobile user. On the other hand, the S1 location, have only one mobile user left. So the system destroys the cache instance in this location, and the remaining mobile user is screamed with the cache instance in central. Through this example, we see that the VCN system follows the end users. And with this concept, we come up with an architecture that first targets the mobile network. This architecture has three important building blocks. The first one is the mobile network infrastructure. It has three different parts. The radio access network, which is typically the connections between the mobile user and the mobile base stations. The second one is the core network, which handles the control plane of the network. And finally, the data gateways, which is called UBF in 5G, which handle the connections between the mobile user and the internet through the mobile network. The second building block of the architecture is the edge platform that are distributed across the mobile network. In this example, we have three different edge platforms. We also call it cloudless. S1 on the top, S2 on the bottom left, and Central on the bottom right. In this cloudless, there are edge enabler functions. For example, ECAM, ECP, ECVM. I'm not going to detail its functionality, so you can read the paper later on. However, they basically help to instantiate the virtual applications anywhere and anytime. And finally, a virtualized CDN infrastructure that can be deployed on the top of the edge platform. In this cloudless, we can deploy a cache instance which comprises one cache controller instance and one or several cache server instances. We also need a cache orchestrator in the central cloudless because this is the brain of the VCN systems. And I'm going to explain this functionality in the next slide. The cache orchestrator has three important pillars: the network discovery, cache management, and traffic steering. The cache orchestrator needs to know the available cloudlets, its location, its coverage, capabilities, status, and so on. So this network discovery allows the orchestrator to build the network topology and to know where it can deploy the cache instance. The orchestrator also manages the life cycle of the cache instance, such as instantiation, terminations, based on the different application metrics, such as the number of screen sessions, energy consumption, and so on. We relied on three complementary mechanisms for traffic steering: traffic influence, traffic rules, and IBNE cache. Traffic influence is used by the orchestrator to tell the mobile network to forward the traffic from the mobile user to the target cloudlet. It is based on the 3GPP traffic influence API. On its cloudlet, there are a lot of different applications, for example, CDN, AR/VR, IoT, and so on. So when the traffic from the mobile user arrives at the appropriate cloudlet, thanks to the traffic influence API, the traffic rules is used to tell the edge platform to forward the traffic from the mobile terminal to the appropriate application instance located inside the cloudlet. The idea of IBNE cache is that every cache instance within the mobile network has the same IP address, so that the mobile user is not aware whether it's streaming with the cache instance in one particular cloudlet or another ones, so that we can steer the traffic behind the scenes based on the application logic. Let's take a look on the workflow to see how the whole system works. At the beginning, there's one mobile user located in the S1 locations, and he's streaming with the cache server instance in central, with the destination IP address ABCD, for example. Later, the cache controller informs the orchestrator about the streaming session, such as service ID, location, bandwidth, and so on. At some point in time, the orchestrator decides to instantiate a cache instance in advance, and then it will send a request to the ECAM. The ECAM then forward this request to the ECPM located in the H1 locations. The ECPM then instantiates a cache controller and a cache server. When the instances are up, the cache controller sends a CAFIT through API saying that for destination IP address ABCD, please forward to the cache server instance located inside the same cloudlet. And when everything is ready, the cache orchestrator informs the orchestrator that it's ready to serve the content. The orchestrator now sends the CAFIT influence API saying that for destination IP address, please forward to cloudlet H1. At this time, the traffic from the mobile user is steered from the cache server instance in Central to the cache server instance in H1 seamlessly using the same destination IP address ABCD. We have built the system to experiment the concept, and the elements to build the system are described in the paper. So in this figure, the blue light indicates the number of streaming sessions served by the cache instance in Central, and the red light for H1. At the beginning, the number of streaming sessions served by the cache instance in Central climbed from 0 to 3, and that triggers the cache instantiation procedure. It takes a little while for the cache instance in H1 up and running, and so at around 80 seconds, the 3 streaming sessions served by the cache instance in Central are seamlessly relocated to the cache instance in H1. Later, we stop progressively 2 streaming sessions, so there's only 1 remaining session served by the cache instance in H1, and that triggers the cache termination procedure. But before terminating the cache instance in H1, the system seamlessly relocates the remaining streaming sessions to the cache instance in Central. We also experiment with the handover and found an implementation issue with .js player. We know that the handover may cause the packet loss, especially the impact might be important if it happens at the end of the media segment delivery. In this particular case, the .js player expects to receive more data of that media segment, but the data were lost during the handover, so it may lead to the playback stall from time to time. We look at the code and found that .js player doesn't monitor well the download progress of the media segment. That's why we propose adding a timer to monitor this download progress from the last data arrival event of the media segment. So, and if this timer is expired, the player should abandon the ongoing segment and ask again for the same segment, maybe with the lowered resolutions. We created a pull request in GitHub, and it was accepted. In conclusion, we have built a fully virtualized CDN system that are deployed on the private Kubernetes clusters. Later, we also ported our implementations to be deployed on the public cloud. Last but not least, our system is applicable to both mobile and fixed broadband networks. So please come and see us at the demo booth and for further details. Thank you for your attention, and I'm happy to answer any questions.
Thank you, Tuan. Any questions in the audience? Okay, thank you again.